All right, I'm excited to go through this with you guys. This thing's pretty cool. It took me a while to make it, but it's worth it. So, okay, nerds, let's put our heads together. We can figure this coupling out. Well, it turns out the NMR nerds were not working out of their garages like my scenario was when I looked further into it. But the Silicon Valley area close to us over near Stanford did have some companies start out of their garages. You may have heard of them, Hewlett Packard or HP, with a total assets 2019 of 33.46 billion HP. And then Google started out of a garage too. It's actually the company is Alphabet Inc. And total assets of 219 in 2019 are $275.9 billion. Google. And then Apple also started out of the garage. Total assets in 2019, 338.5 billion. So I Googled those using the, Google to do that. But I'm not sure. I've heard Apple's $1 trillion company, but I don't know if that's total assets, but whatever. They're rich. They're big companies. So Apple started out of Steve Jobs' parents' garage. Here it is in this picture, where Steve Jobs grew up. He was adopted actually as a kid, as an infant. Okay, now enough with the computer nerds, back to NMR nerds. So here is, I'm gonna butcher the name, Isidore Isaac Rabbi. He was actually born in Europe, in what now is Poland area, to a, what do they call it, conservative Jewish family. And wait, there's another term for that. Not conservative, but whatever. He was a baby when he came to the United States, and he grew up in the New York area. And he got the 1944 Nobel Prize in Physics for discovering NMR, nuclear magnetic resonance. So he's like the godfather of NMR. And he also worked on the Manhattan Project with all those brilliant scientists during World War II. They came up with the first atomic bomb. And then we have here a Swiss-American physicist, Felix Bloch, and American physicist Edward Mills Purcell. They kind of at the same time came up with ways to make NMRs much more practical and much more useful, and had better techniques. And they got the 1952 Nobel Prize in Physics for creating new, much improved NMR methods. Then another Swiss physical chemist, another Swiss. This is Richard Robert Ernst. He was born in Switzerland, but he also worked in the Bay Area as well. He got the Nobel Prize in 1991 for creating what's called a Fourier Transfer Nmr. I've mentioned that a little bit, or it's referred to as a pulse NMR. We'll talk more about that. And what that is it increases the NMR's precision by a lot, or the signal to noise ratio is like 100-fold better. And the signal to noise ratio, what is that? That means like when you're looking for a peak, it's much higher than the random noise underneath it. Okay, so Fourier transform improved NMR sensitivity up to 100-fold. Made this discovery while working at Varian Associates in Palo Alto, California. So Varian is a company that makes NMRs and computers and things like that. And they're in Palo Alto, which is Silicon Valley. So Varian was one of the first Silicon Valley tech companies, actually, before Google and Facebook and all the rest, and Apple. So mentioning the computer nerds like Steve Jobs of Apple was not totally random, because Clara Jobs, Steve Jobs' mom, she actually adopted him as an infant, was a bookkeeper at Varian. It's pretty cool how all this ties together. And also almost all of these companies and people tie back to Stanford. Stanford is a big part of the booming Silicon Valley area. Okay, enough history. Now back to trying to figure out coupling. So imagine Isidore has a simple molecule in a strong magnetic field, and he shoots radio waves at the molecule, and they were absorbed. And he's like, wow, cool. It ate the radio waves. This is so cool. And the simple molecules made singlets. A little more complicated molecules had their signals split, like coupled. The NMR nerds had to put their heads together to figure this out. Imagine you're in this nerd pack, no pod, no, I got it, nerd nest. Say you're in this nerd nest. Let's try to explain the coupling seen in the ethyl bromide from earlier that we were looking at. So here's the proton or H1 NMR of ethyl bromide again. You can see we've got a signal A, the more downfield one. We assigned here as this 2-hydrogen quartet. And then signal B is more upfield, 3-hydrogen triplet. Got our TMS to reference to 0 point. All right, so and this was an SDVS spectra I took and I added TMS to it. That's a 90 megahertz NMR. So let's look at it more closely and make some guesses. So here's our molecule, ethyl bromide. Now we'll draw in its hydrogens. So we know from our bond line structure studies that the terminal line is CH3, this is CH2. If you're not so good at noticing that this has 3 hydrogens and that has 2 hydrogens, and you're like, wow, I didn't know that. You should actually pause now and go back and click through the bond line structure thing, because you need to be strong at that, because that's just the language we use now. Okay, so the 2 hydrogen signal in the middle there, that's a quartet, 2 hydrogen quartet. And the 3 hydrogen signal on the left there, that's a 3 hydrogen triplet. So we're going to try to guess and figure out why one's a triplet and one's a quartet. So let's imagine we're in this nerd nest and we're trying to figure it out. Does anyone have a guess here? Milhouse, is that you? What's your guess? There's Milhouse. Maybe the 3 hydrogen signal is a triplet because it has 3 hydrogens. You get it? If it's 3 hydrogens, it's a triplet. Maybe, huh? Because 3 hydrogens, triplet, 3 and 3. Okay, Milhouse, let's check that with the 2 hydrogen signal. If you're correct, Milhouse, then a 2 hydrogen signal should have a doublet, should have 2 peaks. But look at that. Oh no, 2 hydrogens made 4. Good guess. But yeah, shoot, it's not quite right. That's okay. Any other guesses out there? Oh, well, my mom still says I'm cool. You are cool, Milhouse. All right, and then, all right, we'll need more guesses. So, oh, Milhouse, what do you got? Well, the 2 hydrogen signal is a quartet. Maybe your signal is split twice as much as your number of hydrogens. 2 hydrogens times 2 is a quartet. And that is true, Milhouse. Does this work for the 3 hydrogen signal? So 2 hydrogens times 2 is 4. 3 hydrogens times 2 would be 6, but is this split into a 6 peaks? No, it's not. Darn, the 3 hydrogen signal is split into 4. A quartet, not a, when you have 6, it's called a sextet. So that's not it, Milhouse, but good try. Okay, Sierra nerds, got any ideas? Try to think of a pattern to explain this. So if you want, pause the video for a second and just try to take a guess at it. After a few minutes, if you don't have any ideas, that's okay. But if you have some guesses, write them out, think about it, and then come back and start the video again. So go ahead and pause. Okay, welcome back. So here we go. The number, I'm going to start giving you some hints on this. The number of equivalent hydrogens in a signal's grouping doesn't seem to explain the coupling. So that's what Milhouse was guessing, but it doesn't seem to work. Maybe it has something to do with neighboring hydrogens you have. So neighboring hydrogens saying, for example, this signal is a quartet. Maybe it has something to do with the ones next door to it. So let's see. This 2 hydrogen signal has 3 neighboring hydrogens, right? These are the 3. And the 3 hydrogen signal, this guy's 3 hydrogen signal, has 2 neighbors. Is there a pattern there? Let's see. Before I summarize it, if you already have an idea of how it works, just keep going. But if you're still guessing, why don't you pause the video and think about it for a second. See if you can figure out what's going on. Okay, here we go. So let's look at this. 2 hydrogen signals. The 2 hydrogen signal has 3 neighbors, and it results in a quartet. Then our 3 hydrogen signal, the 3 hydrogen signal for this guy, it has 2 neighbors, and what does it wind up being? A triplet. Do you see a pattern there? Do you see a pattern here? What is that, Lisa? What's that, Lisa? Oh, Lisa's got something to say. The pattern is clear. You get split 1 more than the number of neighbors you have. Oh, that makes sense, huh? So 3 neighbors, I get split 1 more, 4, quartet. 2 neighbors, I get split 1 more, 3, triplet. That seems to work, Lisa. Is that what you were thinking? Yeah, 3 neighbors, 3 plus 1 is 4, quartet. 2 neighbors, 2 plus 1 is 3, triplet. Ooh, I like it, Lisa. You're a genius, you got it. Okay, most people call this actually the N+1 rule. If you Google search that with the billion-dollar company, and you'll find lots of people talking about the N+1 rule. The signal is split N+1 times, and N equals the number of neighbors you have. Okay, looks like we have a nice pattern to try and explain the coupling for ethyl bromide. Let's check to see if this pattern applies to other molecules. So here's another common organic molecule, ethyl acetate. Let's check out its spectra, or first let's predict its spectra. So this is a 3 hydrogen grouping here, right? Those 3 hydrogens are equivalent. And we got another 2 hydrogen group there, it's equivalent. And finally another 3 hydrogen group. Of course, there's no hydrogens on the carbonyl carbon because it has 4 bonds already. All right, this 3 hydrogen group has 2 neighbors close to it. See, it's got these 2 neighbors right there, right? Do you think, so I can see them definitely being neighbors to this and coupling it. But what about the one over here? Do you think that one will couple? Do you think these 3 hydrogens way over here are going to be considered neighbors? Well, let's look at the spectra and see what it tells us. So here's the Proton Nmr Spectra, H1 NMR Spectra of ethyl acetate I got from STBS, and I added the TMS signal in there. So let's label them again, A, B, C, TMS, and I always like to start left to right, A, B, C. And so, continue here, that's a quartet, A is a quartet, B is a singlet, C is a triplet. So if this 3 hydrogen group only has the 2 closer hydrogen neighbors, what should its signal look like? If these are the only neighbors it has, it just has 2 neighbors, what's the N+1 rule tell us? Let's see, N+1. So we have N would be 2. So 2 plus 1 is 3. Oh, I was going to write 3 there. Oh, triplet. C is a triplet. So it doesn't appear that these are neighbors because we have a triplet right here, huh? This signal here looks to be right there, 3 hydrogen signal. And now what about this guy? How many neighbors if this 2 hydrogen group only has the 3 closer neighbors right here, what should it look like? So if it's following the N+1 rule, it's 3 plus 1 is 4, which is a quartet. Do we see a quartet? We do. Signal A is a quartet. So it looks like, yep. It appears these are too far away from there to be neighbors. So these guys are neighbors, but this one's not. Let's continue on with that one then. So if this one has no neighbors, has 0 neighbors, what should its signal look like? N+1, 0 for N, 0 neighbors. It would be a singlet, and B is a singlet. So there we have it. This looks like it's working, huh? So it appears the 2 hydrogen, 3 hydrogen groups are not close enough to couple with this guy. So we can say that signal B is caused by this 3 hydrogen singlet on the left, and then signal A is caused by the 2 hydrogen quartet here. And then these hydrogens show up as signal C, the 3 hydrogen triplet. Pretty amazing, huh? You can just look at these lines on a spectrum and get information about the structure of molecules. All right, it turns out neighbors need to be close enough for coupling to occur. So remember before we said these were too far away to couple? Turns out neighbors need to be close enough for coupling to occur. How close? Well, if they're 3 bonds or less away from each other, they will couple. Let's check this with the ethyl acetate from above. So here it is again, the ethyl acetate and its coupling. So we'll start with signal B, the 3 hydrogen singlet on the far left, this one. So if I redraw the ethyl acetate and I add on some representative hydrogens, I'm throwing the hydrogens for signal B on there and the ones for A. And they're both tetrahedrons because those carbons have 4 atoms attached to them. If this tetrahedron's throwing you off, pause this and go watch the bond line structures in 3D video or click through the Google slide animation. Okay, so we'll use this hydrogen as a representative of B's 3 equivalent hydrogens. This hydrogen is the same as those other 2 because there's rotation around this sigma bond, so they're spinning around and they see an equal equivalent environment. All right, so I'm going to count along the bonds from that hydrogen. So I'm going to say that say I'm a little guy and I'm walking across this bond, I have to walk across one bond, a second bond, third bond, fourth bond, and then a fifth bond. So we saw that B is a singlet, meaning that they're too far away. So it looks like 5 bonds is too far away to couple. And if I counted from, this one or this one to say this one or this one is still 5 bonds away. So like 1, 2, 3, 4, 5. Okay, so signal B's closest neighbor is more than 3 bonds away, 5 bonds, so they don't couple. Signal B has 0 neighbors, lives out in the boonies. So in the n+1 rule, I'll do it again, n equals 0. 0 plus 1, n plus 1 is 1, so that's why it's a singlet. All right, let's look at another one. So let's check signal A, the 2 hydrogen quartet here. So A is here, B is here, C is over there, and we've already seen that it's 5 bonds away from signal B, so we just need to check signal C's hydrogens. A lot of H's and C's, sorry. So let's do that again. Now count the bonds between A and C. So from A to C, we'll use this hydrogen as a representative of A's 2 equivalent hydrogens. So if I go from here, I can go 1, 2, 3. It's 3 bonds away. Just 3 bonds away. They're neighbors and they couple. The other equivalent hydrogens of carbon are also 3 bonds away. So if I counted, say 1, 2, 3, you can see it's still 3. So we can, I can go like this too, 1, 2, 3, like that. Or I can count this one, 1, 2, 3 over here, right? There we go. Okay, so the 2 equivalent hydrogens of signal A have 3 neighbors. So with the n+1 rule, n equaling 3, you have 3 plus 1 is 1. That's a typo, it should be 4. I'll fix that real quick. 3 plus 1 is 4. All right, there we go. And I'll quickly catch up. See, if you guys want later on your practice, you can click through these as fast as you want. So 4 is a quartet, and that's what we saw in the spectra. So let's do some more practice counting bonds. Let's make sure you fully understand the details of this. There's some more details to go with this as well. I think it's best to see them in examples. So bond length affects this counting. What do you think is longer, a single bond or a double bond? What's your guess? What's a longer bond, a single bond or a double bond? If you intuitively guess that a double bond is shorter, you're right. Double bonds are shorter and stronger bonds than single bonds. So here are some approximate carbon-carbon bond lengths. So a single bond, which I'll represent as a single line, it's about a single carbon-carbon bond. It's usually about 154 picometers. Remember, picometers are 1 meter is 10 to the 12 picometers. They're tiny. I used to think maybe when you're 12 years old, if you're in 7th grade, you get picked on by the 8th graders. So that's like picometers, you get picked on. I don't know if that helps you remember. So a double bond, it's a little shorter. So see how I drew the double bond and I made it shorter? And they come in at about 134 picometers. Then how do you think a triple bond would fit into this group? Do you think it would be longer than the other two, shorter than the other two? What's your guess? Triple bond is shorter, about 130 picometers. I'm sorry, not 134. So I bet you guessed triple bonds are the shortest. They are the shortest and they're the strongest. Okay, let's do an example. Before we start our counting practice, we need to talk about one other type of carbon-carbon bond. There's such a thing as partial double bonds. It's in between a single and a double bond. So this happens because of resonance. You can describe this with resonance. A benzene ring is a perfect example of this. So here's benzene. You've probably seen that before. And at first glance, this benzene ring appears to have half carbon-carbon single bonds, like this one, and that one, and half carbon-carbon double bonds. It looks like, oh, that's a double, that's a double, that's a double, right? single bond there, double bond there. But if it were the case that the benzene ring had full single bonds and full double bonds, then it would have two different carbon-carbon bond lengths. It would look something like this. It would have longer single bonds and shorter double bonds. But it turns out the chemist who discovered the ring nature of benzene was August Kuckel. You might have heard of Kuckel structures, like Lewis structures and Kuckel structures. Here's August Kuckel. I need to capitalize that K. Here we go, here we go. I'm gonna find mistakes throughout this, aren't I? You guys find mistakes too, let me know, I'll give you extra credit. So Kuckel was really into mythological Ouroboros Jormungandr. He liked these, I can't even say it, Ouroboros, those things. They're pretty cool. They're these like dragons that can bite their tail, like they make them ring. And this particular Ouroboros, however you call him, is meant to, his name is Jormungandr, is said to be the son of Loki and Angrboda. Those of you who have read the Percy Jackson books probably know all these names. Okay, there's supposed to be the this creature is the son of the Loki. Crazy, huh? So, and the legend has it, he grew so large, he encircled the world biting his tail. He couldn't encircle the world biting his tail. Okay, so Kuckel was getting burnt out trying to come up with a structure for benzene. So he decided to take a break, probably like you when you're studying sometimes and your brain's just not working anymore and you're like, oh, I got to take a break. I got to do something else. He went over and he smoked some opium. He loved opium. Took a nap and had a dream of a snake eating its own tail, like this Ouroboros. He woke up from his trippy dream and he worked all night to use his dream inspiration to determine the ring structure of benzene. So this inspired him, he said, to come up with the ring structure of benzene and moves chemistry along. Experimentally, we find that all of the carbon-carbon bonds are equal bond lengths. They aren't like shorter double bonds and longer single bonds. This confused chemists when it was first determined. Erich Kuckel, a professor of our NMR nerd, Felix Bloch. He's so Felix Bloch we saw earlier helped improve the NMR. He was a student of Kuckel, and they came up with a theory to explain these bond lengths. It involves a molecular orbital theory, and that's something you may have heard of in general chem, but if you haven't, it's okay. We're going to go over that later in the semester, but I'll just mention it here. And so here's Kuckel, Felix's teacher, and there's Felix we saw earlier in our NMR nerd nest. It's kind of cool how it all ties together. So Felix said his teacher, Kuckel, incited and helped his students write poems about their greatest professors. So this is a poem they wrote about Erwin Schrödinger, like you probably heard of Schrödinger's equation and Schrödinger's cat and all that. So at first, here's the German version of the poem that Kuckel and some of his students wrote, and then Felix, who was a Swiss American, he could speak German as well, he translated it to English, and he said, Erwin, he's talking about Schrödinger, Erwin with his psi can do calculations quite a few, but one thing has not been seen, just what does pi really mean? Not pi, psi. So it's referring to Schrödinger's equation, and that's that crazy equation that describes particles as having both particle properties and wave properties, and light having, well, I think it describes light as well having wave properties and light properties. So it's a particle wave duality craziness. All right, so okay, back to benzene and all of its equally length carbon-carbon bonds. Besides Kuckel's molecular orbital model of the bonding, another model, resonance, something you've heard of, can describe the bond lengths. So the resonance of benzene can be seen as the pi bonds of the double bonds equally shared around the ring. So here's our benzene ring. I'll count around the ring. It's got 6 carbons. And I like to think of the pi bonds swinging over on a hinge like this. So I'm throwing in this gold hinge here. And imagine this is like a windshield wiper going, if it's hinging there. So instead of being a pi bond between 1 and 2, it's switching over between 1 and 6. All right, and then imagine this hinge is a door or a windshield wiper or something. And then you throw in another hinge here at 5, and you could swing that bond over that pi bond between 5 and 4. And then you put a third hinge at 3, and you can see that pi bond hinging over between 2 and 3. And in our class, we'll refer to these hinges as Roach hinges for Katie Roach from last year. She got these named after her. All right, so here's the Roach hinge. So we're going to show our resonance arrow. So if you've done resonance before, you should have a double-headed arrow here. And here it is. So notice how the pi bonds have shifted. So in the first resonance structure, we have a pi bond, a double bond between 1 and 2. But now you have a double bond between 2 and 3. Also, we had a single bond between 2 and 3, but now it's a double bond. So resonance is just a tool. It helps us understand aspects of bonding and also reactivity of molecules. It's only a tool, though. It's not really reality most of the time. Well, it can kind of be closer to reality or further from reality. So we don't think of the molecule as switching back and forth between resonance. Like, you know how I'm saying this is a hinge going back and forth? We don't really think that happens, but I think it's just a good visual to help you draw the resonance structure. We believe actually the molecular orbital theory is much better. Molecular theory of modeling? Huckel's molecular theory. Oh, another one. I think that's probably wrong in multiple ones, huh? Oh, of course it doesn't all fit now. 11, would that work? Yeah, there we go. We'll go with that for now. All right, so back to where we were. So the molecular orbital theory is a better model, but it's not as easy to use. So we're going to use resonance because it's real helpful. But we can use resonance structures to envision a resonance hybrid that is closer to the reality of the molecule. So this is our resonance hybrid. And so instead of drawing the two resonance structures, we kind of combine them. And we show dotted lines for the pi bond that's being shared. The dashed lines is used to represent partial pi bonds. So instead of thinking of each of these as a double bond or single bond, think of them each as like a 1.5 bond, because they're like half pi. The pi's are being shared, and then full singles. So yep. All right, so now back to the carbon-carbon bond length discussion. So remember how we said single bonds were the longest, double bonds were shorter, and triples the shortest? Where should we put the partial double bonds, like in benzene? How would they fall on this list? What do you think? I bet you guessed the correct answer. It's between the single bond and the double bond. So we have our single bond as before, 154 picometers. The partial double bond, which we're going to show as a dashed and a solid line, that's about 140 picometers. And finally, the full double bond is shorter again. Not finally, but it's shorter again. It's 134 picometers. Triple bond is the shortest still, 130 picometers. So that's pretty cool, huh? So when you get a full double bond, it gets shorter. If you have a partial double bond, it gets shorter than the single, but not quite as much because it's only partial. All right, so now you're an Mi6 agent with a license to kill the coupling distance concept. Are you ready? Dun, 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 dun. So let's practice counting bonds and predicting if they're coupling or not. So here we are. Bond, James, 1, 2, 3, sometimes 4 bonds. So coupling can occur through 3 bonds or less. Coupling through 4 bonds can happen if bonds are shorter. So we haven't seen that yet, but we've seen the 3 or less, huh? So 2 bond coupling. Here's a molecule. First off, though, can these 2 hydrogens couple? But wait, before we answer that, are they equivalent? So is this hydrogen equivalent to that? You'd think they would be. They're both attached to the same carbon. But are they? No, they're not equivalent. One is on the same side as the chloride, This one's on the same side as the chloride, and this one's further away from the chloride. It's dashed away from us. So they're not equivalent, so they could couple, or they possibly can couple. Let's count the bonds between them. So it's 1, 2 bonds. They only separated by 2 bonds. Should they couple? Yeah, they're 2 bonds away from each other. That's less than 3 even. They can couple for sure. All right, now next up we have 3 bond coupling. So these 2 hydrogens here, can these 2 hydrogens couple? Well, let's count the bonds and see. So we'll have 1, we'd have to imagine you're a little miniature guy and you're walking along this bond. I walked along 1 bond, 2 bonds, 3 bonds. Okay, there I am. So 3 bonds away. Should it couple? Yes, 3 bonds away is close enough. They will couple. Next up, 4 bonds. So here we are. Can those 2 hydrogens couple? So let's count across. 1, 2, 3, 4. Okay, so they're 4 bonds away, more than 3. If they were 3 or less, we say yes, for sure they couple, but now 4. I don't know. But as you count though, you go through this short double bond. Remember the single bond's longer than the double bond? So this is a shorter one. So I have like 2, well, between the 2 hydrogens, I have 2 carbon-hydrogen bonds. They're always present. But then the carbon-carbon bonds we have to consider. We have a long carbon-carbon bond here, a single one, like that. And then we have a short double bond, like this. So we went through a shorter bond. Is that going to get these 2 carbons close, or 2 hydrogens close enough to couple? Yes, experiments show they do couple. So having that double bond in the chain makes them close enough. All right, let's do another 4 bond coupling. So here we go. These benzene ones can be tricky at first. If you guys are having trouble with these, just ask me. We'll run through a bunch of examples and you'll get it. Can these 2 hydrogens couple? So how far apart are they? 1, 2, 3, 4. Okay, they're pretty far apart with 4. They're more than 3, so let's think about it. As you count through the path, you have these 2 medium length partial double bonds. So remember, these are actually the partial double bonds. It looks like a double bond, single bond, but that's not the case. Remember, we should look at the resonance hybrid to see those. But okay, first off now, 2 carbon-hydrogen bonds always present. So let's kind of not worry about those. We're going to focus on these medium length carbon-carbon partial double bonds. And to make sure you understand that, remember this is a resonance hybrid we need to consider. So don't forget Kuckel's opium-induced dream. Benzene rings, carbon-carbon double bonds are all partial double bonds. So let's draw the resonance hybrid to make sure you're not thinking these last arrows we're pointing at a full single bond and a full double bond. So there it is. See, I just added in there. I'll spin it around, make sure you see what's going on. So these are partial double bonds, partial double bonds. Okay. So do you think the partial double bonds shorten the path enough to allow coupling through 4 bonds? They do. Experiments show that those will couple. So having 2 of those like medium length partial double bonds will get you to couple at 4 bond distances. All right, now we'll stick with the same molecule, and it's called toluene, by the way, but we'll look at a different pair of hydrogens. We'll be using toluene. That's a common organic solvent in chemistry, organic chemistry. 4 bond coupling again. So now we're going to look at these 2. They look really close. They're close in space, but let's count along the bonds. So can they couple? Let's go 1, 2, 3, 4 bonds away. Okay, so 4 bonds away. We saw you can get 4 bond coupling if some of the bonds are shorter. Let's see what we got here. As we count through, we get the 2 CHs, and then we get a long single carbon-carbon, and then we get 1 partial double bond, and that's it. So, and remember, the singles are long, partials are shorter. So 2 carbon-hydrogen bonds always present, and a longer carbon-carbon single bond. And here we have the medium length carbon-carbon partial double bond. So do you think that having just 1 of these shorter carbon-carbon partial double bonds shortens the path enough to allow hydrogen coupling through 4 bonds? It does not. We don't see coupling between these 2. When you take an NMR of toluene, which you guys will hopefully in the spring, you'll see this is a 3 hydrogen singlet. It doesn't couple. All right, so one more easy example, then we'll summarize this stuff. So here we have, this is actually a 3-carbon alkane. That's the propane, like in your propane barbecue tanks. So can these two hydrogens at the end couple? They're separated by 1 bond, 2 bonds, 3 bonds, 4 bonds. So they're more than 3 away. And then did you pass through any short bonds? Nope. You just had the 2 carbon-hydrogen bonds, which are always present. And then you have the 2 longer carbon-carbon single bonds. So do you think those will couple? They don't. We see no coupling between these 2 hydrogens, and I hope you would have guessed that, because that's even a further distance than the one prior with the just a partial double bond, 1 partial double bond in the path. All right, so let's summarize these so it makes sense to you. So as we go through this, count the bonds and make sure I made no mistakes. So here we go. When you have 2 bonds between your hydrogens, say for example these 2 hydrogens, 2 bonds apart, so you should count with me 1, 2 bonds, right? Detail, count that they are 2 bonds apart. Yeah, when you're clicking through this on your own, make sure you confirm that. And then will coupling occur? Yes, they will couple. Wait, and then are they equivalent or are they different? They are not equivalent because this dashed hydrogen is closer to the bromide and this wedged hydrogen is further. All right, now 3 bonds. Let's look at this example. We've got these 2 hydrogens we're considering. How far apart are they? 1, 2, 3 bonds away. So should they couple? Yes, they should couple because they're just 3 bonds apart. And then when it comes to 4 bonds, we've seen that sometimes they couple, sometimes they don't. What about this one? How many bonds away are the 2 hydrogens? They are 1, 2, 3, 4 bonds away. But their path includes a short carbon-carbon double bond, a full double bond. Will they couple? Yes, they will couple. This shortens its path enough. All right, another 4 bond example. We're going to look at these 2 hydrogens on a benzene ring. And then as you go through their path, you have a 1, 2, 3, 4 bonds, right? And you have your 2 carbon hydrogens, they're just always there. And then you have a partial double, 2 medium length partial carbon-carbon double bonds. What do you think? Will coupling occur? And I'm throwing in the hybrid so you can see that these are partial double bonds. Yes, they will couple. Good. And now for the next one, we'll compare these 2 hydrogens. How many bonds apart are they? 1, 2, 3, 4 apart. But as we go through the paths, you see you have a long carbon-carbon single bond and then a medium partial double bond, but that's it, only 1 of them. So should they couple? What did we see earlier? No, they will not couple. They're too far apart. In this example, we went through 2 partial double bonds, and this one you only went through 1 partial double bond. All right, now finally the last one we saw, these 2 hydrogens, they are 4 bonds apart, 1, 2, 3, 4. And the path does not include any short bonds, so no, they won't couple. Okay, so you see how this is the point where the coupling ends. If you have 2 medium length partial double bonds, you will get coupling. If you only have 1 of them, none. And if you have no short bonds, none. So that's the key thing to remember. You just have to remember 2 medium length bonds. You can get coupling. Only 1 medium length you won't, and if there's no short or medium length, you won't get coupling. All right, so here's a nice summary of that. 2 to 3 bonds between the hydrogens, they will couple. 4 bonds, it depends. They'll couple if it's through a full double bond or 2 partial double bonds. And that makes so much sense, doesn't it? Because a partial double bond is like half a pi bond, and if you have 2 of them, then you get a full pi bond. It's just like the same thing. And then usually no coupling if you have 4 bonds away and 1 partial double bond. I say usually because there's exceptions to these, but I'm not gonna like write a problem that just makes you miss because there's exceptions. So, but when we see them, we'll just say, hey, that's an exception. And then if it's 5 bonds or more, you shouldn't get coupling. We will see exceptions. So with an alkyne, the really short one, sometimes you'll see 5 bond coupling, but not always. So, but it's okay. All right. So I'll end this long coupling adventure with a few examples. And actually, I did more examples than I was originally thinking. So that sentence end is not quite true yet, but we're going to click through this first example, see how I format it, and then I want you to try to click through, or try to draw out the other ones on your own. So here we have an ether. This is ethyl Tert-Butyl ether, or Tert-Butyl ethyl ether. I think so, yeah. So let's look at these three hydrogens on the end. That's called a methyl. These three hydrogens of this methyl are equivalent. I'll redraw the molecule over here and add in some hydrogens. So I'm considering these three hydrogens, and I'm going to draw out one of them to emphasize it. There's still two more on here, but I only need one of them since they're equivalent. And I'm going to see how far away they are from these two. So if I count it out, are these two close enough to be neighbors? Yeah, they're 3 bonds away. 1, 2, 3. 1, 2, 3. Yep, they're close enough. So I got 2 neighbors there. Yep, counting across. And then if I 2 and like 3, I can go that one too, huh? And then check the table to the left to see if you have 3 bonds. Yeah, you will couple. And the n+1 rule says if you have 2 neighbors, which we have 2 neighbors that are 3 bonds away. There's a lot of 2s and 3s here, huh? So there's 2 neighbors to this group. And so 2 + 1 is 3. That means this group's going to be a triplet. So that'll be a 3 hydrogen triplet. Okay, let's move down the line. Now we're looking at this one. That's a 2 hydrogen signal. They are equivalent to each other. And if we redraw and we emphasize them, these are the signal hydrogens. This methyl on the left, we already know it couples because we figured it out, right? That's what made this one a triplet. There's 3 bonds away. So if I'm 3 bonds away this way, I'm 3 bonds away that way. So I don't have to like talk about that. I just know I have 3 neighbors over here. What I do have to check though is over on this side, on the right side. I got no hydrogens there because that carbon has 4 bonds, but then each of these carbons has 3 hydrogens. So I'll draw out one of them. Let's see how far away it is. It's 5 bonds away. So if I count from this one, say 1, 2, 3, 4, 5. So if it's 5 bonds away, will these be considered neighbors? No. So only the 3 hydrogens of the methyl will couple with these 2 hydrogens. So only these 3 neighbors. So it has, using the n+1 rule, it has 3 neighbors, n = 3. So 3 + 1 is 4. So it is a quartet. So we label this one as a 2 hydrogen quartet because it has the 3 neighbors. 3 + 1 is 4. All right, next up, there's no hydrogens here, so we'll skip over that one. These methyls are all equivalent. And there's 9 hydrogens there because each methyl has 3 hydrogens. And this single bond right here, it can rotate. So it's not like this methyl is closer to this ethyl and that's further. It is in a moment in time, but as they're spinning, they average out where their position is. So 9 hydrogens are all 5 or more bonds away from other hydrogens, so they do not couple. We already established these are too far from this guy, so they're too far from that guy. And you should double check. I'll do it right now. 1, 2, 3, 4, 5. Yeah, there's 5 away from that. And then 1, 2, 3, 4. Wait, no. 1, 2, 3, 4, 5. No, I forgot the hydrogen. Okay, there'd be a hydrogen here. It'd be 1, 2, 3, 4, 5, 6. Yep. So n+1 rule has 0. These 9 hydrogens have 0 neighbors. So 0 + 1 is 1, so it's a singlet. And then that signal is a 9 hydrogen singlet. All right, we're getting it. So that example wasn't too bad. Let's do another. So get out a piece of paper and pencil and try to do this one on your own before you watch me do it, or if you're clicking through, before you click through. So here's the molecule. Pause the video and see if you can first circle your groups of hydrogens and then predict how many neighbors they would have and what their coupling would be. Okay, so did you pause the video? All right, now you can come back. All right, so we have these 2 hydrogens over here. Those 2 methyls are equivalent. This sigma bond here, the single bond, can rotate. So it's not like this methyl is closer to that all the time and that's further. They're rotating. Okay, so now, yeah, this means the 2 methyls can spend equal time next to the ethyl right of them. Do they have any neighbors that they couple with? Let's redraw this over here and add in a representative hydrogen off of that methyl and then a representative hydrogen there for its closest neighbor. Can these two couple? They're 3 bonds apart. 1, 2, 3. So yep, they will couple. N+1 rule. There's just one neighbor there. So, oh, it'll be 1 + 1 is 2. It's a doublet. So this guy is this signal, these two equivalent methyls, 6 hydrogen doublet. We'll see a lot of this, the common feature in organic molecules, these 6 hydrogen doublets. All right, next up, this single guy here. How many neighbors does this one have? So I redraw it over here where I make its hydrogen red, and then I'm going to check both sides. But initially, I know these 6 hydrogens, these 2 methyls, are neighbors to this because that's why that's a doublet, right? So I don't have to count any bonds there. I already know this couples with those 2 methyls. Does it couple with this other one, though? Yes, it's 3 bonds away. 1, 2, 3. So it'll couple there. So there's actually, I drew out 1, but there's 2 hydrogens on this carbon, of course. So this guy has 6 hydrogen neighbors to the left, these ones, and it has 2 hydrogen neighbors to the right. So it has a total of 8 neighboring hydrogens. It's a lot, huh? So what's the N+1 rule tell us then? If N equals 8, it's 8 + 1 is 9, and we actually call that a no net for 9. I'll give you a summary of what the terms we use for these. It's not like something you have to take time to memorize. We'll use it so much it'll just stick. And if you, for whatever reason, forgot no net and you said it's split in 9 places, I'd be like, that's fine. You know what it looks like. There's a little more to this story, though. There's something interesting about this one. So the 6 neighbors to the left over here, they're different than the 2 neighbors to the right. And if all of your neighbors are not equivalent, so these 6 neighbors are equivalent to themselves, but they're not equivalent to the 2 over here, then you usually don't get nice clean splitting. I'll show you what that means later, but you can get a signal that doesn't look like a clean no net. And in these cases, because of that, I want you to put a question mark by your predicted coupling. So this is what I mean. And that question mark signifies like, it might be a no net, I don't know, like kind of like that. So I'll show you what I mean. So we're going to label this as a 1 hydrogen no net. Kind of go high pitched like you're not sure. I don't know, maybe. It's probably not looking perfectly like a no net. It might look real close, but it might look really random. So that's how we'll label these things. If your neighbors are not equivalent, like this guy has some neighbors here and some neighbors here, and they're not exactly the same, I'll put the question mark, and I'm going to say I think it could be a no net, but it might not be. All right, next group. There's a 2 hydrogen signal there. Those 2 hydrogens are equivalent. How many neighbors do these guys see? So I'll redraw it. We know that it sees the 1 neighbor there because it's 3 bonds away, and we already established that. And then what about these 2? Do they couple? They're 1, 2, 3 bonds away. Yes, they do. So I've got 1 neighbor on this side. So this 2 hydrogen group has 1 neighbor to the left and 3 to the right. Remember, this is a methyl. So how many neighbors total does it have? It has 4 total neighbors. So what's the next question do I ask after now I know how many neighbors total I have? I want to ask, are all 4 neighbors equivalent? Is this single neighbor here equivalent to this methyl? No, the neighbors are not equivalent. So what do we do about that? We're going to put a question mark by our prediction of the coupling. So if you have a total of 4 neighbors using the N+1 rule, it's 4 + 1 is 5. It's called a pentet, but we put the question mark there to say it's like that one's a 2 hydrogen pentet. You're not sure? Maybe not. I'm gonna guess it might look like a pentet. These 2 neighbors might be similar enough that it can still look like a pentet, but might not. All right, so yeah, the different neighbors, they couple a little differently, and we're going to talk more on this later. And if I think I'm actually going to put in my spectroscopy intro a link if you want to look ahead of schedule and see why that happens, the question mark when the neighbors are different. You can check that out. So next up, the last one here on the end. So we already established this is neighbors with the methylene on the left, that one. So it's got those 2 neighbors. They're 3 bonds away. And the 2 hydrogen neighbors, are they equivalent Yes. So we expect a clean coupling and no need for that question mark. So using the n+1 rule, 2 + 1 is 3. I'm expecting a triplet. So it's a 3 hydrogen triplet, not like a triplet. Not sure. No, I feel confident it's a 3 hydrogen triplet. You can say it in like a demon voice to show like you really mean it. That's a 3 hydrogen triplet. All right. So done. That one was a bit tricky though, huh? The neighbor's not equivalent and all. If the neighbors are not equivalent, then you may not get the coupling predicted by the n+1 rule. Actually, the coupling will usually not be as predicted when the neighbors are not all equivalent, and we'll discuss why this is later. Now, for another, the more of these you see, the easier it becomes. All right, here we go. We got one with the benzene ring. So first off, I'll point out carbons without hydrogens. So we're gonna no hydrogens on that carbon, no hydrogens there, no hydrogens there. So those ones are easy. And then these 3 methyls are equivalent. Let's look at them. Redraw the molecule. Are these close enough to couple? Let's see. It goes through a 1, 2, 3, 4, 5 bonds. 5 bond path. It's not even 4. I would say I don't even have to consider whether the bonds are pi bonds or anything. That's just too far away. So I'm going to say no coupling for that. So that this 9 hydrogen group has no neighbors. And so the n+1 rule makes it 0 + 1, which is a singlet. So that there is a 9 hydrogen singlet. Actually, it's silly to call it a singlet like that because there's no coupling, so it's never going to be a question. All right, so here we go. Then these 2 hydrogens are equivalent. A lot of times in the beginning, students think like these are equivalent, but they're not. Like this hydrogen is right next to this, what's called a Tert-Butyl. This hydrogen is right next to the Tert-Butyl. They're both kind of far from the ethyl, kind of far. So those are equivalent. I got a 2 hydrogen signal there. Let's look at their coupling. So we already know that they don't couple to this guy because that's 1, 2, 3. There's no hydrogens there. 4, 5, too far away. And they won't couple here because there's 1, 2, 3, 4, 5 bonds away, too far. So then we don't have to worry about that. Often students get confused about these though, and they think maybe this hydrogen couples with that one, but let's not think of a coupling between hydrogens that are equivalent. Since they're both equivalent, let's not consider them neighbors to each other right now. So the 2 equivalent hydrogens are 4 bonds away. So like they are 1, 2, 3, 4 bonds away, and they go through a partial double bond. So you think, oh, they're close enough to couple, but because they're equivalent, let's say they don't couple. Okay, so here we go. Will these couple though? How far away? They're 3 bonds away. 1, 2, 3. So yes, these 2 will couple. So this hydrogen will only sees this one neighbor. So it's going to be split into a doublet. I'm pointing this out because a lot of times students get confused because this hydrogen sees one neighbor, that hydrogen sees one neighbor. So they think, oh, they got 2 neighbors, but it's not like that. This is how it works out. This hydrogen here only sees that neighbor. This hydrogen doesn't see that one. So it's split into a doublet as well. And since both of these hydrogens are equivalent, they overlap at the same parts per million on an NMR spectrum. So for example, added my NMR parts per million here at scale. All right, so this hydrogen right here, it's going to be a 1 hydrogen doublet. This hydrogen right here, oh crap, I screwed that up. This should end over here. Boom, there we go. Yeah, I could edit this out. We'll see if I edit this out of the video. It makes it more human if I don't though, right? Ugh. All right, here we go. So, that hydrogen is a 1 hydrogen doublet. Then this hydrogen is a 1 hydrogen doublet that shows up at exactly the same spot. So when we look at the spectrum, we see them as a 2 hydrogen doublet. So 2 hydrogens make a 2 hydrogen doublet. So I'm going to say this one more time because people get confused with this one. So here we go. So this hydrogen couples with that hydrogen. This hydrogen couples with that hydrogen. But this hydrogen does not couple with that one. It's too far. 1, 2, 3, 4, 5. So he's only seeing one neighbor, and he's only seeing one neighbor. So I think of each as a one. This is a 1 hydrogen doublet, and that's a 1 hydrogen doublet. So this 1 hydrogen doublet, boom, shows up there. This 1 hydrogen doublet, boom, shows up right on top of it. The area is doubled, and that's why we call it a 2 hydrogen doublet. Whew. All right, so there's our 2 hydrogen doublet. And then we've got another 2 hydrogens here next door, and they're equivalent as well, just like the pair to the left. And can they couple over here to this ethyl? Let's look. So can this hydrogen reach over to there to couple? Let's see, they're 1, 2, 3, 4 bonds away. They go through 1 partial double bonds. 1, 4 bonds away, only 1 partial double bond. They do not couple. So this guy does not couple to the ethyl, and of course it won't couple way over there. It's only going to couple to its other benzene ring hydrogens, so it's going to be a 2 hydrogen doublet as well. We're going to see this motif a lot, a benzene ring that has things attached to it on opposite sides of it, and then it makes a 2 hydrogen doublet, 2 hydrogen doublet. All right, and now finally, getting down to the end here, we got this 2 hydrogen signal here. Those 2 hydrogens are equivalent, and they are not going to couple into the ring. We've established that that's 1, 2, 3, 4 bonds away with only 1 partial double bond. Won't happen. But it will couple this way, right? Because it's 1, 2, 3 bonds away. Yep. So it's got 3 neighbors there. So 3 plus 1 is 4. It's going to be a quartet, 2 hydrogen quartet. Hopefully this is getting easier for you. And then this last one's pretty easy. Those 3 hydrogens are equivalent. And the methyl couples with the methylene to its left. So the methyl is a carbon with 3 hydrogens. The methylene is a carbon with just 2 hydrogens. So they will couple. And so this methyl has 2 neighbors, plus 1 is 3, so it's a triplet. So that one's a 3 hydrogen triplet. All right, we got it. So here are some Proton Nmr splittings we'll see this year. These are the clean ones, the ones when all of the neighbors are equivalent. So if you have 0 neighbors, you're a singlet. You'll look something like that. We call it a singlet, and we use the letter S to abbreviate it. If you have 1 neighbor, you're split into a doublet, you know, the n+1 rule. And it looks like this. They're usually about equal height and area. So you use D to represent that. And then if you have 2 neighbors, you'll get a triplet, and it's usually the center one is the tallest. And we use T. We'll talk more about why, like this, the area ratio of these is 1 to 3 to 1. And then this one, when you have 3 neighbors, you're a quartet. And you have this shape where you have the 2 outside ones are the same height, it's approximately the same height area, and the middle ones are approximately the same height and area. And that's quartet Q. Continuing on, if you have 4 neighbors, you're a pentet, P. 5 neighbors, sextet. If you called it a sextet or, I don't know, a hextet, I'm okay. But usually people refer to that as a sextet. And then 6 neighbors, n+1, you're a septet. 7. 1, 2, 3, 4, 5, 6, 7. And then if you have 7 neighbors, you're an octet. 1, 2, 3, 4, 5, 6, 7, 8. And finally, 8 neighbors, you're a nonet. And there 9 neighbors, you're a decat, but we won't really see that. So 8 neighbors, 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. And you got N. And you have 1 letter abbreviations for these guys, but except for the sextet and the septet, because you already use S for singlet, but it's okay. And these things, don't feel like you have to like, oh, I got to make flashcards and memorize it. Don't worry. We'll be using them a lot, and it'll just, it's like language. You'll just pick it up. All right. So, okay, now for a few more quick examples without discussion, making sure you agree with my predictions. So get out some paper and a pencil. try to do these on your own before you click through my answer key. All right, here we have a ketone. So pause the video, try to predict this, and then come back and watch my answers. Okay, welcome back. So we've got the two methylenes in the middle here. They're equivalent, and that's a 4-hydrogen quartet, because this 2 hydrogens will see 3 neighbors. They won't see these neighbors, they're too far. And these 2 hydrogens will see its 3 neighbors, but not those. So they're each going to be, this will be a 2-hydrogen quartet. This will be a 2-hydrogen quartet. They'll be at the same chemical shift, same parts per million, so it'll be a 4-hydrogen quartet. And then the outside methyls are equivalent, and there'll be a 6-hydrogen triplet because they each will see 2 neighbors. So this is a 3-hydrogen triplet, 3-hydrogen triplet, they overlap, 6-hydrogen triplet. All right, now this is a ketone that's a constitutional isomer or structural isomer of the last ketone. It's not as symmetric. See how that affects things. So we got a 3-hydrogen signal here, right? And it's a singlet because it's too far to couple for these guys. So let's see, 1, if there's a hydrogen drawn out here, 1, 2, 3, another hydrogen, 4. 4 bonds away, all single bonds. All right, and then this one is a 2-hydrogen triplet because it can't reach to couple there, but it couples to those 2 neighbors. 2 plus 1 is 3, triplet. And now this one, it's got 2 neighbors here, 3 neighbors there. Are these 2 neighbors equivalent to those 3 neighbors? Nope. So 2 neighbors, 3 neighbors, 5 neighbors total. This is a 2-hydrogen sextet. It might look like a sextet, probably not, because these neighbors are not equivalent. They're going to be coupling differently with this signal. All right, and the final one, it's a 3-hydrogen signal. It can only reach to these 2, so that's going to be a nice 3-hydrogen triplet. All right. Now we got another aromatic ring. So this is toluene again. We talked about this a little bit, but we'll do the full spectrum of it now. This is a benzene ring with one thing attached to it. You can refer to it as a mono-substituted benzene. We're going to see this a lot. So this one has a methyl here, but if there's a bromine here or an OH here, it's going to have similar coupling through the ring. You're going to see over and over, so try to make sure you understand this. This one, it's pretty tricky, but if you're not getting it, just ask for help. So we got the first 3-hydrogen singlet because this neighbor and this neighbor are too far apart. 1, 2, 3, 4. And it only goes through a 1 partial double bond. Then this 2-hydrogen signal, it's a triplet. Get my lung workout. Make me COVID strong. Just kidding. So here we go. Let's see how it's a triplet. So it's got 1 neighbor. It's got 1 bond, 2 bonds, 3 bonds. Okay, that's definitely a neighbor. And then 1 bond, 2 bond, 3 bond, 4 bonds away. Can this hydrogen and that hydrogen couple? They go through 2 partial double bonds. So yep. So it's got a neighbor here closer and a neighbor further. They're going to couple differently. So it's probably not going to be a triplet, but that's why we'll label it. And then we have this one here. How many neighbors does this have? It has, counting from here, 1, 2, 3. That's definitely a neighbor. 1, 2, 3. Definitely a neighbor. Is this a neighbor? No, it's equivalent. So it's just got 2 neighbors, and they're not equivalent. So that's a 2-hydrogen triplet. All right, so this guy, how many neighbors does it have? It's definitely got these neighbors. 1, 2, 3. 1, 2, 3. And they're equivalent, so that's good. But wait, can it reach all the way up here as well? Let's see. 1, 2, 3, 4. Oh, yeah, it's 4 bonds away. We already know it reaches because this is a triplet. So because it went through a partial double bond. So this guy can couple to these 2 and those 2. Now these 2 are equivalent and these 2 are equivalent, but these 2 are not equivalent to those 2. So all the neighbors are not equivalent. So the 4 neighbors for this guy make it a 1-hydrogen pentet. Okay, so now this one, we got this single hydrogen here. And how many neighbors does it have? Let's see, can it couple to these guys? 1, 2, 3, 4 bonds away, and it's through a partial double. Yeah, it can couple to that. And then 1, 2, 3, 4. Yes, it can couple to that. Are these 2 equivalent? No. So that one's a 1-hydrogen triplet. Okay, this one. It's a 1-hydrogen quartet. So why is that? Because it can couple to this one. 1, 2, 3, 4. It went through 2 partial double bonds. And it can couple to this one because that's only 1, 2, 3 bonds away. And it can couple to this one because it's 1, 2, 3, 4 bonds away, but through 2 partial double bonds. So it's seeing all 3 neighbors, and they're not equivalent, so that's the question mark. Quartet. Now this one, it can definitely see 1, 2, 3, that neighbor. 1, 2, 3, that neighbor. Can it see this neighbor? 1, 2, 3, 4, 5. Nope. So it's only seeing 2 neighbors. And are those 2 neighbors equivalent? No. So that one's a 1 hydrogen triplet. And this one is the same as this one. It's a 1 hydrogen quartet. Because it can reach to this neighbor, it can reach to that one, and it can reach to that, and they're all different. Whew, that was a hard one. This kind of NMR spectrum just comes out a big mess. All the peaks are overlapping. But I want you to be able to predict them. All right, so if any of these were confusing again, just ask me for help. Come to my Zoom session. We'll get you solid. If you come to a Zoom session and I give you like 3 or 4 examples of this, I find out exactly where you're getting confused and I get you over the hump, you're good to go. All right, so a couple more and then we'll be done. So this guy, try to do it on your own and then come back and look at my answer key. Okay, here we go. Those 2 in the middle, those 2 methylenes in the middle are equivalent. So that's a 4 hydrogen doublet because this 2 hydrogen sees the 1 neighbor there. Can't see that neighbor. It's 1, 2, 3, 4 bonds away, all single bonds. So this guy sees a 1 neighbor. It's a 2 hydrogen doublet. This guy sees its 1 neighbor. It's a 2 hydrogen doublet. They overlap, 4 hydrogen doublet. A lot of times students want to think of this coupling with that, but they won't because they're equivalent. Next up, the 1 hydrogen here and the 1 hydrogen there. These see a lot of neighbors. We'll use this as a representative. It sees 3 neighbors there, 3 neighbors there, so 6. And then it sees 2 neighbors here, 7, 8 total. And are they equivalent? Is this neighbor equivalent to that? No. So this one's got 8 neighbors. It's a 2 hydrogen no net. All right, finally the methyls on the outside, they only see the 1 neighbor there. This is too far away. 1, 2, 3, 4, yep. So each methyl sees 1 neighbor, so it's a 12 hydrogen doublet. Whew. All right, this guy, this one's got some symmetry. This is nice, huh? This molecule is called Metazylene. So here we go. The 2 methyls are equivalent. Can they couple into any of the benzene ring hydrogens? Let's see, 1, 2, 3, 4 bonds away, only 1 partial double bond. Nope. 6 hydrogen singlet. Then this one here can't couple to the methyls, but can it reach these guys? Let's see, 1, 2, 3, 4 bonds away, but it went through 2 partial double bonds, so it can couple to this one, and it can't couple to that one. 1, 2, 3, 4. So that one's a 1 hydrogen triplet. And I'm saying triplet like that because this hydrogen neighbor is equivalent to that one. They're not different. And we'll see that because we're going to circle them, huh? So those 2 are equivalent. How many neighbors do they see? We just established it can couple that far. There's no neighbor there, but it can also couple here. So it's got 2 neighbors. So it's a 2 hydrogen triplet. This one, whew, I'm tired. We got some hydrogens here. It's a 1 hydrogen triplet because it has this neighbor and they're equivalent. And it can't reach that far. 1, 2, 3, 4, 5, too far. All right, we got another ether. This is methyl Tert-Butyl ether. Mtbe, this is a fuel additive. Makes gasoline burn cleaner. Okay, so this guy's got 3 methyls on it. So it's got a 9 hydrogen signal, and it's a singlet because they're too far from the methyl here. 1, 2, 3, 4, 5 bonds away. So this is an easy one. So 3 hydrogen singlet because it's too far. And then we have an aldehyde to end it off. It's got the 1 hydrogen here. Seems like that wouldn't couple with these for some reason, but let's count the bonds. 1, 2, 3. Oh, it will. It's only 3 bonds away. So that's a 1 hydrogen triplet. This guy here, it's got the 1 neighbor there, the 3 over there, 4 total. 2 hydrogen penta. This one, 3 hydrogen signal with only 2 neighbors. That's the 3 hydrogen triplet. Whew. So again, confused, especially like the ones that usually trip people up are these middle ones And then the benzene always trips people up. Just ask me for help. Oh, that was a long one. Took me so long to make this and to make this video. To make the Google slide took me like, I don't know, 15 hours. It took forever. But now that it's done, you guys can use this and really get a lot out of it. If you've listened to the whole video, you can listen to it again, but you might want to just go through next time and click through the Google slide animation on your own. I think it's more interactive. You'll be making these type of coupling predictions all year. It'll become second nature. You'll get really good at it. And while you're considering the structure of the molecules during this process, you'll be improving your comprehension of the bond line structures and the geometry of organic molecules. And this is going to really help you for the rest of the year. I used to teach this stuff in like later in the semester, and then I realized if I teach it right away at the beginning, then everything else is easier in the course. So that's why you guys are lucky to get my teaching in my, what is this, my 19th, 20th year or something, or 18th, I don't know, it's been a long time. But I keep learning new things, and hopefully these will help you. So welcome to the NMR Nerd Nest. You are full-fledged members now. This singlet welcomes you. Our doublet welcomes you. I'm pulsing with excitement to welcome you, the Pulse NMR guy. And welcome. And if you want, you can come to my house. My mom's making Chex Mix, and we're going to play some D&D. So Millhouse is inviting you over too. You're part of the club now. Okay, so you can go back to the Proton Spectroscopy Introduction, NMR and IR. See you there.